The receiver operating characteristic. This is a graphical representation of the confusion matrix. It only works for binary classifiers, but it has a very rich history. Let's look at some extreme examples of classifiers. So let's suppose we had a classifier where we labeled everything as positive. Then our little p would be capital P plus n, and little n would be 0. Or we could label everything as negative. In that case, little p would be equal to 0, and little n would be capital P plus capital N. We could label observations using a coin toss. We flip a fair coin, heads is positive, tails is negative. This isn't a good classifier in general, but it is a possible classifier. So we could determine whether something's in class 1 or 0 by simply flipping a coin and, say, looking at the outcome of the coin. The key idea here is we probably want to avoid these kind of extreme classifiers. Now, in order to do that, we're going to look at the relationship between the true positive rate and the false positive rate. So if all the observations are classified as positive, then the true positives equals the positive, the false positives is the negatives, the true positive rate is 1, and the false positive rate is 1. If everything is classified as negative, then the true positives and false positives are both 0 because everything's negative. So the true positive rate is 0 and the false positive rate is 0. And now let's look at our random classifier. If we were to use a coin toss, then on average half of the positives would be labeled negative and half of the negatives would be labeled positive. And that would give us a true positive rate of 1/2 and a false positive rate of 1/2. And in general, and we'll actually see this later on, we could look at the same idea only using a coin that's biased, so there's a probability of Q, which is not necessarily 1/2 of getting a heads. Now let's see if we can visualize this TPR FPR relationship. We're going to put the true positive rate on the vertical axis and the false positive rate on the horizontal. And then we're going to draw a grid. The ideal would be for the true positive rate to be 1 and the false positive rate to be 0. And so the green point at 0, 1, true positive rate equals 1, is our goal. It's the ideal. If we're extremely positive, then both our true positive rate and false positive rate are 1. If we're extremely negative, they're both 0. If we're extremely random, they're both 1/2. And we can see that we can break up the unit square into the upper half is where the true positive rate is greater than the false positive rate, and the lower half is the opposite. And certainly you would imagine we'd really like to be up there in the green where the true positive rate is greater than the false positive rate. So remember, 0, 1, that's the ideal point. Now let's suppose we looked at an extremely random classifier in which we had a coin with a probability of heads being Q. Then that means that the QP positives would be labeled positive and QN negatives are also labeled positive, and so therefore the true positive rate and the false positive rate would both be Q. And that would be on the line TPR equals FPR. So since this is true for all Q, we can see that this dotted line, this dotted diagonal, which corresponds to true positive rate equals false positive rate, corresponds to a random classifier. Now, we have at this point the random classifier line and the 0, 1 ideal. The reality is that the true positive rate at best is only going to be approximately 1. The false positive rate is approximately 0. Now we're going to use F to denote the actual false positive rate and T for the true positive rate. So that point there has coordinates F, T. And we're going to connect that point with a line that also connects the two non-random extremes. Now the curve that we get is called the receiver operating characteristic. Why the receiver operating characteristic? Well, you remember a minute ago we had actually a picture of people working with radio headsets. So the receiver operating characteristic actually emerged in World War II as a way of analyzing radar and radio communications, of saying how good the radio signals were. Now the area under the receiver operating characteristic, notice it's a union of a triangle and a trapezoid. So there's our triangle and there's our trapezoid. The area of the triangle is a half, f times t, and the area of the trapezoid is the average of the two sides times the distance across, which is 1 minus f. And if we expand that and then simplify, we get t over 2 plus 1 minus f over 2. Well, 1 minus f, if you'll remember, is the specificity, and t is the sensitivity. So the area under the curve is the average of the sensitivity and the specificity. Or we could write it like this: 1/2 Tp over P plus Tn over N. Now if P is approximately N, the number of actual positives is approximately the number of actual negatives, then we have a total number of observations of 2P, and therefore we have the area under the curve is essentially the sum of the true predictions over the total. So what does that mean? That means if P is approximately N, the area under the curve is the probability of an observation chosen at random being correctly classified. So that relates it in a probabilistic way to something that's essentially the same thing, which is the accuracy. In general, the area under the curve is the probability a classifier correctly differentiates between a randomly chosen pair. So if you randomly chose a pair and you knew that one was positive and one was negative, the area under the curve would be the probability that the classifier would differentiate between the two correctly. So let's look at our getting dessert example. So we're going to do this with rattle, and you'll notice I've already loaded the data for us, and notice I put in a partition of 80/20 and I execute. Now let's just go through and see what all we can do. We can explore the data. Let's just generate some summary statistics, some ideas describing the data set. For example, the number that get dessert versus the number that don't get dessert in the training set in this case. We can also do some tests. These are statistical tests. We can do transformations, normalize, recenter, so on and so forth. We can do some clustering. We can do rule association. And then here are our models. In particular, we've already selected a tree model. So our getting dessert data gives us a tree model that looks like that. This is for 80% of the data. Now let's evaluate that. So we go to evaluate, and let's first look at the error matrix. And you'll notice this is actually the confusion matrix, and the lower one is in percentages. So we get error, and that gives us our accuracy, and neither one of them are very good. The receiver operating characteristic we get by executing there, and you'll notice that the receiving operating characteristic is almost that diagonal line. The area under the curve is almost 0.5, so we're almost got a random classifier with this getting dessert example. So in summary, receiver operating characteristics are a good tool for estimating how good a classifier is at predicting the class of an unlabeled observation. Now the receiver operating characteristic, and in particular the area under the curve, it's really only reliable if the number of positives is about the same as the number of negatives. We'll look at that in the exercises. could be misleading if you don't have this. We'll also see that the receiver operating characteristic is a good tool for comparing two classifiers for the same set of data.